Alright, let's continue. Okay, let me open the table of content first. Okay, we are on chapter 18, still on chapter 18, and still on homework simulation here. Yeah, let me open that. Okay, we are in this section. We have to take a look at question 1. Oh yeah, basically this section is, what is it called? It's about a simulation to see how translation from virtual address to physical address works with linear page table, which I assume we have other type of page table later on, maybe something like that. But for now we are taking a look at the linear page table. We already take a look at question 1. I already take a look at question 2. And now we are taking a look at question 3. To be precise, in this simulation configuration. So let me open that. I think I have some info here. Okay. Wait, let me check this. So to remove virtual page from virtual address, we can use this maximum value as the page mark. Not, wait a minute. Isn't the page mark? Oh, wait, let me check. Page mark getting the offset, right? So to remove virtual page number bits from virtual address, we can use this maximum. Okay, maybe. Basically, we are using this one, the maximum value that the page bits can hold. And then, yeah, using this as a max to remove the virtual page number bits, something like that. Where is it? I think something like this. Right. Oh wait, no, not that one. This one, offset. Okay. So we have virtual address here. We are using page marks. And then we are removing this one. let's try the simulation, I guess. In Beijing, page size 1K, address size 16K, and then physical size 32K, verbose and the use address space 75%. Okay. We have this one. Wait, first thing first, virtual page number. We got the virtual page number. Okay. I am still not sure if we need to add this one into the virtual page number max, and why not just using the complement of page mark? Yeah, I'm still not sure about that. So let's try using the complement of page mark, something like this, and then redshift to get the bits. Yeah, something like to get this first 4 bits, right? Redshift by 10 because this is 1K. Okay, 10 bits. Okay, yeah, something like that. Right, maybe. Anyway, we got this one. Okay, 11. Virtual page number 11, and then page frame number. Okay, we have this one. I think we can just remove this. Maybe. I'm not sure if that is correct. I mean, basically we do this, right? We are removing the leftmost bit because the leftmost bit is the valid bit, so we are not using that bit as the page frame value. We are using the rest of the bit. Okay, something like this. Okay, 19. Alright, page frame number 19. Okay, wait a minute. We need the offset now, and we got the offset by removing the page, what is it called, the the virtual page number bit, something like this, using this as a max. Okay, let me show this, I guess. Oh, interesting. Wait a minute. Okay, we have this one. Oh, right. It is this one, right? So we are removing this. How many characters is this? I assume this is 14, okay. Can we do something like this? Okay, right. We are removing the 4-bit, the leftmost 4-bit here, and only get this bit, right, as the offset. And we got this number 527. And now we need the base frame address from the base frame number. Base frame number 19, left shift 10, okay. 19456, okay. 6. The last one is adding the bit from the base frame address, from the offset into the base frame address, something like that. The offset, okay, something like this. 19983. Alright. So the next one is this one. Virtual page number. Okay, complement the page max. Okay, something like this. Oh, right. We also need to right shift because this is the base address for the page table, something like that. And then to get the virtual page number or the index, we need to what is it called? We need to remove the extra bits. Again, this one. We need to remove the extra bit and only get this bit. Alright. By 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, okay. It is 9. 9, 10, 11, 12, 13. Oh, okay, 13. It might be something like this. So if we right shift, we will get this one. Let me check. Yeah, we got this as the virtual page number bits, the binary digit 6, okay, and then page frame number I think let me check that. One. Is it gonna be the same if I do this? Okay, at least for now it is the same. Yeah, I'm not sure if this representation is the same as this one, the binary digit like this. Okay, and then offset. To get the offset, we need to remove the virtual page number bits, the opposite of this one. Okay, something like this. Okay, let me show you what it looks like. Okay, not that one. Something like this. So basically we are removing this one. Wait. The 4 bits here, and only having this one. Okay, this is the offset bits, which is equivalent to this one, 390. And then we need to get the base frame address, basically the base address for this page frame number. If you remember this, previously I create the page table with the range, something like this. So this is the base address for this page, and this is the maximum address for page 7, for page 10, something like this. So what I mean by this base frame address is basically getting this base address for the page number and then adding the offset bit on top of it to get the exact address for the page frame address, the real physical address, something like that. Okay, 31. Wait. Okay, I think 10, right? Okay, and then it will become something like this. Yeah, basically we got this, right? left shift that by 10 bit. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. 10 bit becoming something like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What is this? Oh, 14, okay. Alright, so we left shift by 10 bit, getting this one as the base address for the page frame or the physical frame there. And then we need to add the offset bit into the base frame address, something like this. What is the offset again? Okay. And then we got this one, 32134. Okay, let's continue on to the third virtual address here. Okay, what is the virtual page number here? Okay, this is the one. Oh wait, no, this is the base address for the virtual page. Now we need to remove the offset bit here. Yeah, let me show that again, I guess. We need to remove this one and only get this. So we need to right shift that by 10 bits, and well, become something like this. And this is the virtual page number, something like that. Okay, 13, and then the page frame number, this one. Okay, let's try this, I guess. 27, and now let's try removing the leftmost bit, because you know the leftmost bit is the valid bit, right? Something like this. Okay, it is still 27. Yeah, I'm kind of curious. Is removing the egg here, right, and only getting this one always equivalent to the value, like removing the one bit here and only getting the rest of the bits or binary digit. I assume it is not always the case, but yeah, I'm not sure. Now to get the offset, is is it? Okay, 514 marks by, okay, page mark here. The maximum, what is it called? The maximum value that can be held within the page size, it is 1k, and 1k in here means 1024, not only 1000. Something to keep in mind. And the bits is from the exponent of 1024, something like this. This is where we get the page bits or the binary digit. Alright, and well, if we have this one, okay, we have 11 bits, not 10. See, this is 11 and this is 10. I assume that's why we use this one, page size -1, as the masking to get the offset, maybe. And then the base frame address, or the base address for the page frame or physical frame, something like that. 27 10-bit, okay. 27 648 offset. Okay, now we are adding the offset bits to the base frame address, something like that. What is the offset again? Okay, 202. Alright, so it becomes something like that. Hello, Sir Roti. Welcome. Okay, we are currently still on chapter 18, in case anyone new here, still on the homework simulation in this book, Operating System TECPs. Basically trying to check how the virtual address translate to the physical address with the patching technique with linear page table, basically something like that. Okay, CPR PNK, hello. A power of 2 -1 will give you just a bunch of ones. Oh, okay. The power of 2 -1. I assume something like this, right? Like a bunch of ones. Okay. Yeah, that is something to keep in mind. Okay, we got this one. Yes, okay. Now let's continue into this virtual trace. Yeah, I'm trying to translate this manually. Well, I'm not sure if this is manual if I use the Python interpreter. So let's just assume this is manual, I guess. Okay, right, this is 10,240. If we take a look at this, what is it called? The range in the page table, I assume this one will be in the virtual page 10 because we got the base address 10,240, which is on the virtual page number 10 or the index 10 here. But let's verify that. Redshift by 10 bits. Yeah, we got 10. Alright. Virtual page number 10 and then page frame number. Page frame number, this one. Okay. And then 3. Alright. I think this is page frame 3. Yeah, I mean, if we represent this as binary digit, right? It's basically only this one. This is just, what is it called? Extension or maybe padding, something like that. So we can just take this and we get the same decimal number here. So yeah, this is the page frame number 3 with the offset. Okay, 947, masking by this one. Okay, 707 here, and then we need to get the page frame address similar to this one. The page address in the page, right? This is the, what is it called? This is the page table, the virtual page table. So this is the page address in the virtual page, and the PFA here, or page frame address, is the page address in the physical page, something like that. So we need to get 3 left shift by 10. We got this one. Okay, 72, and then adding to space address bits with the offset. What is the offset? Okay, the offset is this one, and then become 79, something like this. Wait, what? 18? Oh, interesting. 18. What is the virtual page number here? Zero, okay. Virtual page number 0, and it is valid again, right? Page frame number 24 with the offset okay. Oh, wait a minute. Okay. I mean, I don't think we need to redshift this one, because I assume it's gonna be the same, right? Okay, offset 18. So the base address is 24576, something like this. Adding the bit here. Adding the offset 18. 24594. Something like this. Is that i3wm or swing? This is the i3 window manager. So what distro are you on? I'm currently on Arch Linux. Yeah, this is Arch Linux with i3 window manager, something like that. Okay, let's try if our calculation correct or not. Virtual page. Okay, let me put this in here. Virtual page number 11, right? And then 19983. Okay. Alright. The next one is 32134. Okay. And the virtual page number 6. Alright. This one, and then the next one is virtual page number 13. I mean, something like this with the physical address 27850 here. Okay, and then the next one is virtual page number 10. This one, with physical what is it called, with physical address 3779. Okay, the last one with virtual page number 0, right? and the physical address 24594. Okay, something like that. Okay. Oh, same. Alright. Fellow Arch Linux user, I assume. Okay. Let me try this last configuration, I guess. Is it gonna be different? I don't think this is different, right? Virtual test 18, then 947, something like that. And the base table also the same, because again with the 75%, all of these page table are already valid. So I don't think we need to calculate that again. Okay. What happens as you increase the percentage of pages that are allocated in each address space? Well, as we increase the valid address also increase, I guess. In this scenario, right, with the page size 1K, the address space size 16K, and the physical address and the physical space size 32K, 75% of it basically make all the address valid, all the virtual address valid. So before 100% usage, we are already have the virtual address valid, all the virtual address valid at the 75% usage. Okay. Now let's continue into the question 4. Now let's try some different random seed. Okay. And some different and sometimes quite crazy address space parameter for variety. Which of these parameter combinations are unrealistic? Why? Okay. Parameter combination are unrealistic. Okay, this one is the, what is it called? The page size of 8 byte, I guess. And this one is 32 byte. Assume the address space size and the physical memory is 1K byte. Which of these parameter combination are unrealistic? Unrealistic. I mean, I think from this one, unrealistic. Maybe this one. Having the page size 1 megabyte or 1 megabyte is a lot, and the address space is also quite big, like 256 megabyte for one address space. I mean, if I understand correctly, each process has its own address space. So having an address space of 256 megabyte for one process by default is not what is it called? It's not small, you could say. It is gonna take up a lot of space. So maybe this one is the unrealistic combination, because the address space is too big for one process, and also the page size is too big, which can cause the internal fragmentation. Yeah, maybe something like that. Okay, but let me try this one. What is it called? The virtual page is invalid. Okay. I'm kind of curious if I use this 1K. I assume it's gonna be the same. Okay, yeah. I mean, from the script here, if the last character is K or uppercase K, right, we got this one. The profile size multiplied by 1024. Okay. So this one case similar to 1024, something like this. Okay, let me check that. 14 virtual page number. Oh, the virtual page 0 also invalid, so only this one is valid. Okay. maybe something like this. 6, okay, and then right shift by by 3 bits, I guess. Right, egg, what is it called? Egg byte, maybe something like that. 0, okay. Without bit 0, it is invalid. 20, okay. 20, okay, something like this. Oh, interesting. 2, virtual page number 2, it is invalid again. Okay, virtual address 25, two again, okay. Invalid. 3, okay. Virtual page number 3, 0. It is invalid. Virtual address 0. It's still gonna be 0, right? So every virtual address here is invalid. Is that it? Well, let's find out. Oh, 3. Okay. Wait a minute. Oh, right. Yeah, it is. And -1, not 8. Right. My bad. Yeah, let me revise that. Virtual page number 1, and then this one, 97, page frame number 91, I mean, and then the offset, okay. The offset is 6. Okay. Page frame address 97, F3, okay. Page frame address and the offset here. Alright. Is that true? Okay. 7 make 2. Alright. Okay, now let's try this one. Yeah, I sometimes forget that it is not the exact page size, but page size -1. Okay, 16. Let's shift by 3 to okay. 20, 25. Okay, so page number 3 still invalid. Okay, this one, okay, invalid. Alright, so there is this one, only this one that is valid. The rest is invalid. Alright. Yeah, okay. I think let's continue this parameter combination on the next session. So that's it for now. Thank you for watching and see you next time. Bye bye.